Hey everybody, this is Mr. Johnson. Hope you guys are having a great day. And these are the EL2 notes, so exponentials and logarithms, the second target here. What we're trying to be able to get you guys to do is rewrite exponential and logarithmic equations in equivalent forms. That means actually going back and forth from exponents to logs and from logs to exponents. So it's just this big cycle between the two. So first off, it's important to talk about what those things are. In its simplest form, a logarithm answers this question. How many of one number do we need to multiply up to get to another number? If we are thinking about the words of this question, there are a few things we have to think about. First off, how many of one number talks about an exponent. So how many do we have to multiply? That's talking about some sort of exponent. The number that we are considering, that is the base. And then to get to another number at the end, that would be our solution. So a lot of times we're going to be dealing with exponentials, like 2 to the third equals 8. We have our base, our exponent, and our solution. Logarithms really focus on getting down here to the exponent part, and that's actually really what they're used for. Logs are a way to solve for variables that appear in the exponent position. So whenever we get a letter up here in that teeny tiny font, we're probably going to have to use logarithms to unpackage it and to solve for x. So you can see here, we haven't really talked about where the word logarithm comes from, but it gives us the definition here. It's a quantity representing the power, meaning an exponent, to which a fixed number, the base, must be raised in order to produce a given number. That's literally what this question says up here. This word was made up by the Scottish mathematician John Napier, and he got that from Greek. So logos is where the log part, and that means proportion, or it means ratio, and then arithmos means number. So he has a proportion or a ratio with a number, logarithm, and that's where he got that phrase from. But again, it's to undo exponents, to get in there and to work with those. So let's go ahead and let's look at some practice problems. We're going to have you guys actually try to do this on your own and try to discover a little bit about how to go back and forth, how to translate from logarithms to exponentials, just like how you would translate from Spanish to English. If 3 to the second power equals 9, obviously that's something we all know is true, we can translate that into a log form. All right, as a logarithm, that statement will look like this. Log base 3 of 9 equals 2. All right, and I said that very carefully because there's a way that we need to think about it. But notice we have 3, 2, and 9. 3, 2, and 9 all together. What I would like you guys to do is take these problems here in this table and go from exponential form to logarithm form. Take the 4, the 3, and the 64 and try to rewrite it in logarithmic form, which you will have to use the word log. So keep in mind there'll be a little number down here, a regular number, an equal sign, and then a regular number again. You need to figure out where to put the 4, the 3, and the 64 in terms of those three positions. If you get it wrong, that's okay. We're going to have a spot here so you can make corrections, and so you'll know how to do it correctly if you messed it up, if the positioning was wrong. So I want you to take 2 or 3 minutes, look at A through I, and just try to rewrite it here in the middle with log and the numbers in the different positions. So go ahead and pause this video and try to do that, and we'll see if you guys got them correct. Okay, let's see if you guys did the first one right. So A, the answer to A when we go from exponential to logarithmic form is going to look like this. Log base 4 of 64 equals 3. Okay, so a couple of things to note here. Boink. In the original problem, 4 is the base. 3 is the exponent. And then 64 here, that's the answer, or the solution. When we go from exponential form to logarithmic form, things line up. So we have to have the word log. Obviously, if we're going to logs, there needs to be that word. But the next little number here, that is the base. It's the base of that word. It's a subscript. It's below the word. So log base 4. And then we say of this number that follows. So 64, well, that just correlates to my answer part right here. Now what's left? After the equal sign is 3. 3 happens to be the exponent. The exponent is what we are looking for. So logarithms and exponents, they're on opposite sides. A logarithm is another name for an exponent. How many of those things do we have to multiply up to get there? So if you didn't have that, you go ahead and make that correction over here, okay, and just write down the correct answer. Log base 4 of 64 equals 3. That's how you translate from exponential to logarithmic. So let's go ahead and let's see if B is correct for you guys. It says 2 to the 5th equals 32. Rewriting that in logarithmic form will look like this. Log base, we'll look back here and see what the base was. Our base was 2, so it'll be log base 2. We have 32 is what the solution is, what the answer is. That's right over here. It equals 32, so 32 goes inside the parentheses. And then equals to the exponent. The exponent's always the last thing, and our exponent here was a 5. 2 to the 5th power is 32. So its logarithmic form is log base 2 of 32 equals 5. If you didn't get that correct, you just go ahead and you can mark it right over here. All right, put that answer right there to make sure you have the correct format. You can go ahead and cross off your other answer if you got it wrong. That way you know not to trust it. So there's kind of a nice little trick here that I want to show you to make sure that this makes sense, because there are a lot of positions that you could screw things up with. What I did back in high school to make sure I was doing these questions right was a little bit of a loop. So I start with my base, I loop around through the answer, and then I arrow to the thing inside parentheses. And what that does is it sets up our exponential statement. 2 exponent 5 equals 32. If this does not match up with our original, we made a mistake setting up our logarithm. So it's a little bit of a swirl action going on there. So that's one thing that you can do. And you always need to check to make sure, is that making sense? Is 2 to the 5th power 32? And it is actually. So I'm kind of giving away some of our other answers here. Let's go ahead and let's turn those on and then just flip through them. Oops. With C, I have log base 10 of 10,000 equals 4. Now this is a special one. Oops. This is a common log since it's got a base of 10. All right. You don't have to write 10 down there. It's kind of the default. You'll see that on your calculator a lot. So does that make sense? If I go ahead and do the little loop-de-loop, go around town and end with the inside, 10 to the 4th power equals 10,000. That's exactly what I started with, so it checks out. D, 6 to the negative 1 equals 1 over 6, 1/6. Well, in terms of a logarithmic form, that's log base 6. That's my base. Of 1/6, that's my answer, equals -1, -1 being my exponent. If I tried to do the loop-de-loop swirl method there, 6 to the negative 1 equals 1/6. That checks out with the original problem. E, you should have log base 5 of 1/25 equals -2. Rewriting that, 5, -2, 1/25, it checks out with the original problem. F, it says x to the 6th equals 64. This is one of the first ones where we have a variable, but that's fine. You treat it just like anything else. So x is actually my base, so I will write log base x. And then inside I put the answer, log base x of 64, equals whatever the exponent is. So I look back here where the teeny tiny number is, and it's equal to 6. What that would say if I rewrote it backwards, translating again from logarithm to exponential, going back, it is x to the 6th power equals 64, which is exactly what my original statement is. So you want to double check to make sure if you're translating to logarithmic form and you translate back, it's still the same thing. G, H, and I, last three questions here. 3 to the x equals 81. That would be log base 3 of 81 equals x. The swirl method checks out here. H, 9 to the 1/2 power equals x. Well, that's just log base 9 of x equals 1/2. Now remember, 1/2 as an exponent is just a square root. Okay, so that kind of makes sense. You'd have the square root of 9 equals x. If you were to solve that, which we will eventually get to, x will be equal to 3. And the very last one, e to the second power equals 7.389. E is just a number. Remember, it's painted out in the hallways. So you could write log base e of 7.389 equals 2. The swirl method would check out, as I've written right down here. Or, because it's a special type, this is called a natural log, you can write ln. I usually will do that in cursive so it doesn't look like 1n or something weird like that. So ln meaning the log natural. Natural log of 7.389 equals 2. If you rewrote that with the swirl method, e squared equals 7.389, that is the question that we started with. If for any of those you didn't get the correct answer, go ahead and just write that over here so you'll know for the future. Let's go ahead and let's generalize this pattern. So firstly, when we write logarithms, it will always be a log, a base of an answer equals the exponent. Logarithms are asking about exponents. They're equal. A logarithm is another name for an exponent. So an exponential equation, if we have a very general equation, right over here using only letters, y equals b to the x, b being the base, we can translate that to logarithmic form. If we have the word log, b is its base, y meaning the answer that we would get, it's on its own side, equals x, the exponent. So logarithms and exponents will always be on opposite sides. Hopefully this makes a little bit of sense to you because it can get kind of confusing. We're going to practice several problems here so you can get the hang of it. Let's go ahead and let's turn to page 2. Up at the top, there's a box here for special logarithms. We've actually talked a little bit about this when we were graphing logarithms and exponentials. The special types of logarithms are called a common log, which a common log, again, would have a base of 10. Usually, they will write it just as log with no 10 at the bottom, but you can if you really want to. It's just extra work. The second type of logarithm is called the natural logarithm. Its base is e, which is just a number, 2.7. You could write it as log base e. People don't usually do that. You could write it as log of base 2.7. People usually do not do that either. People usually will use ln, which means log natural log. The first questions here on the second page, we need to write each exponential equation in its equivalent logarithmic form. We're just translating back and forth. So question number 1. 729 equals 3 to the 6th power. In log form, we need to write the word log. The base is 3. That's the big number. I put my answer, which was 729, equals 6. 6 is the exponent. If I did my swirly, 3 to the 6th power equals 729. Question number 2. 1/8 equals 1/2 to the 3rd power. Well, if I'm going to write this in log form, my base here with the exponent is 1/2. So I need a teeny tiny 1/2 here. My answer was 1/8. And then equals whatever the exponent is, 3. If I do my swirl to check it, 1/2 to the 3rd power equals 1/8. That is exactly what this says. Question number 3. 10 to the 0 power equals 1. If I go ahead and put this in, it is log base 10 of 1 equals 0. That's actually one that you could do on your calculator if you wanted to double check that. If we turn on our calculator, there's a button for logarithms. It's right here. Since it says just log, it's a common logarithm, which means it's a base 10. If I go ahead and put 1 in parentheses and hit enter, I get 0 out. Now, some of these other logarithms, I can't do those because they are not log base 10. The only other option I have, unless you have a super fancy new graphing calculator, is a natural log. So common logs and natural logs are the only ones your calculator works in. So with question 4, if I were going to put this in log form, since it has a base of e, I could write log base e, but usually people don't do that. They would write ln of, and then I have to go ahead and put my answer, 20.086 equals whatever the exponent is, 3. Again, we could double check this. Go ahead and put my calculator over there. So I could have the natural log 20.086, press enter, and I get basically 3.0000023000055. And that's just because of rounding. This 20.086 is not the perfect number. It would go on forever, kind of like E does. It's irrational. So let's go ahead and let's look at 5 through 8. We're writing each logarithmic equation in an exponential form. So here we have log 100 equals 2. Doesn't look like there's a base at all. But anytime there's not a base, it's a common logarithm, which means the base is 10. So if I were going to write this, I have to go backwards and put my base first. What's the base? The base is 10. Then I have to go ahead and I'm going this direction. The exponent is 2. That equals, we end with 100. Now, that should make sense. If we get something weird, like it's out of order and it says 100 to the 10th power equals 2, you obviously know that can't work. 10 squared is 100, so it checks out. Let's look at question number 6. Log base 3 of 81 equals 4. Well, the base was 3. 4 is on the outside, equals 81. 3 to the 4th power equals 81. That makes sense because 3 times 3 is 9. 3 times 3 is 9, and if I take 9 times 9, that's 81. That's one of those special perfect numbers. Question 7. ln of 5 equals 1.609. Well, we could rewrite that if we had to as log base e of 5 equals 1.609. So my base here is e. E to what power? E to the 1.609 equals the inside, which is 5. Now, if you aren't quite comfortable with that, go ahead and check on your calculator. So your calculators also have an E button. It's right here above the natural log. So if you press yellow, second natural log, it gets e to an exponent. So we'll just put 1.609, close the parentheses, hit enter, and we get 4.99781, which is basically 5. But the reason we don't get 5 is because of rounding. That 1.609 is not the exact answer. So we get our answer is off slightly. Last one here, question 8. Log base 4 of x equals 3. So 4 is my base, 3 is my exponent, equals x. If I wanted to figure out what x would be, I could solve that. X equals 4 times 4 times 4, which is 64. That's what we're going to be getting closer and closer to here with these targets. Let's go ahead and let's look at question number 9. Can we find the x value needed? So can we actually solve this? So it says log base 2 of 8 equals x. Well, if I'm going to maybe try to change this, I can change it from logarithm form to exponential form. So we would go ahead and do this little curl. 2 is the base, x is the exponent, and I should equal out to be 8. That's my answer. Now, if you know anything about 8, 8's a very special number. 8 is 2 times 2 times 2. If you remember these, 2, 2, 2. So it's equal to 2 to the 3rd power. Now, if you set this up, 2 to the x, and rewrite 8 as 2 to the 3rd, notice what happens with our bases. They're exactly the same. So if the bases are the same, then these exponents should also be the same. So 2 to the x equals 2 to the 3. That means x has to be 3. Now, let's go ahead and let's try to put that into our calculator. So we put log, it looks like there's an 8 in there, and we'll hit enter. We don't get 3. Now, why is that? Well, because our calculator is using a common log, not a log with a base of 2. There's no way I'm going to be able to get a base of 2 in my calculator. It only does tens or e's. This is where we have a special formula to help us out. It's called the change of base formula. We can use this in a lot of different places. It's very important. So it says log base a of x. A could be any number. Could be like 2 from up here. Could be 22. Could be 7. Okay, it's something that our calculator can't do. If we are going to try to change it to something our calculator can interpret, we take log base a of x, and we take the x and put it up on the top of a fraction. Notice there's a fraction bar in here, x is in the top. The a value, which is the base, goes on the bottom. Now when we do that, we actually get to say any base that we want, so long as the base on the top and the bottom are the same. So we're essentially changing it from something our calculator can't do, right there, into two logarithms our calculator can do. So when we choose our new bases, the bases we probably would want to choose would be 10, a common log, or e, a natural log. It doesn't matter which one, you will get the same answer, which is kind of cool. So we can change any bad logarithm into a good logarithm just by doing this change of base formula and making it into a fraction. Let's go ahead and let's apply this to a couple of questions. Number 10, it says x equals log base 4 of 5. So I want to go ahead and just do the change of base formula, because if I tried exponential format, try exponential, it would look like this. 4 to the x equals 5. Now, I don't know if we can get a 5 by multiplying 4s. It's not going to be a whole number. It's not 4 to the first, it's not 4 to the second, nothing like that. So unfortunately, exponential form won't work. Change of base formula will, however, work. So I would have x equals, remember, if the number is more towards the top, it stays on the top of the fraction. So it's going to be a log of probably a base 10, so log with a 5 inside. There's an invisible 10 down there. If the number was more towards the bottom, it's going to go to the bottom of the fraction, so that's going to be a log with a 4 inside. Notice how it's both a base 10 and both a base 10. I can change it to whatever I want. So it can be common logs, it could be natural logs, it could be fifth logs. It doesn't matter so long as they're the same base. Common logs, usually the way to go. So if I go ahead and put this in my calculator, I'm going to get a decimal. What we've done actually already is we've found the answer. Okay, this is the perfect answer. We call that generalized form. It's without any decimals. It's what you're left over when you get x equals. So let's go ahead and let's write that down, and then we'll find the actual decimal. This is a number. Log of 5 over log of 4. Putting this in my calculator, I just have to hit the log button. So that's right down here. Log of 5, close my parentheses, make sure nothing else gets in there, divided by log of 4. If you don't close your parentheses, you start to get weird answers. Press enter. So x equals 1.1609. Again, that goes on forever. So just give me a couple of decimal places, put a couple of dots at the end showing me that it does not stop there, and we're good. Generalized form is the perfect form, and then decimal form is a nice approximation. Let's go ahead and let's try 11 to see if we can do the same thing here. You'll notice it's not just x equals in this. It's x plus 7, which means we're going to have to do some stuff to get rid of that 7. But before we do that, I always like to take these bad logarithms and change them so that my calculator can find that decimal. Log base 2 of 9. Well, I'm just going to have log of 9 on the top, since it's closer to the top, over log of 2. Because 2 is the subscript, so it goes underneath. It's like below the ground. These could be logs of e's, logs of 10s, logs of anything, but log 10, a common log, is the best choice here. So it says x plus 7 equals this chunk. In order to get rid of that 7, you subtract it, and subtract it from the end. So my generalized form, x equals log of 9 over log of 2, and subtract 7 from that answer. Let's go ahead and let's see what that is on the calculator. So whenever you're doing major things, like rewriting this whole big fraction, I like to group that all together in a superior set of parentheses. So this is a logarithm with 9 inside, divided by another logarithm with a 2 inside. And since I have this first parenthesis, I have to close it. That captures all of these things into this one group over here. After that group, I have a minus 7. So that's just subtracting 7, hit enter, and I get negative 3.83. With a couple zeros at the end, dot, dot, dot. All right, right there. So you have to make sure that you understand how to put in your calculator. You also have to understand how to write generalized form. Both are pretty important. We have a couple questions here on the back, and then we are done with these notes. So let's look at question 12. 3x equals log base 6 of 22. Oh, it looks like we got a bad logarithm here. So let's go ahead and let's use the change of base formula. So that's just going to be equal to log of 22 over the log of 6. Both of those are common logarithms. Then I have 3x. Now, if you recall, I need to get rid of that 3 by dividing by 3. But if I go ahead and put that below everything here, it gets a little messy. So I would encourage you guys, think about where dividing occurs. It's technically down here on the bottom of a fraction. So when I divide by 3, it goes on the bottom of a fraction. So it'll go right down here. And when it's down there, it is technically multiplying by that 3 because it's 1 over 3. That's dividing by 3. If I rewrite that, I can rearrange the order down here. So dividing, those numbers always go on the bottom of the fraction. So 3 will be on the bottom. Log with a 6 will be on the bottom. And on the top, I have log of 22. Well, you say, what happens to the 1? Well, what is 1 times anything? 1 times log of 22 is just log of 22. So this is actually my generalized form. X equals log of 22 over 3 log of 6. Could you, if you really wanted to, leave it as log of 22 over log of 6 and then say divide by 3? Sure, that's fine. Sometimes that's nice, but I think if you can stick the 3 on the bottom where dividing goes, it looks a lot better. So let's go ahead and let's figure out what that is as a decimal. So on my calculator, I need log of 22 divided by, and I need to trap everything down here since there's multiple pieces, or else it will just divide by 3. It takes the first thing. Your calculators are pretty dumb. So I have log, and I have a 3. So the piece I still need, log base 6. And I got to have another set of parentheses since there's 1, 2 left-handed parentheses. I need 1, 2 right-handed. And I get 0.5750. I like 4 decimal places, but if you just want to do 3, that's okay with me. I am not fine with just 1 decimal place. That's not accurate enough. So generalized form and decimal form. Question 13. Got a lot of stuff going on here. I also have an imperfect logarithm. It's not a common log, it's not a natural log. So let's use the change of base formula. So I'm going to go ahead, put log of 194 on top over log of 16. The base goes to the bottom. The bigger number goes up top. Then I have x minus 4 and then divided by 5. This can be pretty tough if you don't know how to get rid of that 5. It's not hard, you just need to put a 5 on top. That cancels it out. That's multiplying. So if I multiply by 5 over here, it also goes on top. Now there's a special way that we can rewrite all this top stuff. So I have x minus 4 equals log of 194, but I multiplied it by 5, so I should technically put a 5 out in front. Normally those numbers go first. Divide that by log of 16. So I've just snuck the 5 right up top, kind of like how in the previous problem I snuck the division on the bottom. So how do I get rid of the minus 4? Well, you guys should know how to get rid of subtracting 4. You add 4 and then you add 4 at the end. Now the difference here between adding and subtracting and multiplying and dividing, when I go ahead and do that, I cannot just put this up top. That would divide the 4 by the logarithm, okay, which it is not being divided by that. So I have 5 log of 194 divided by log of 16, and at the end I have plus 4. That is our generalized form. So I'll go ahead and just place that right up there. Now what is that as a decimal? As a decimal, it's not hard to find. I have to go ahead and wrap all this first chunk in big parentheses so it does it all at once and it doesn't screw with the 4 at the end. So 5 times log of 194 divided by log of 16. Got to close the parentheses so it keeps it all as one group, and then at the end, that's when I get to add 4. Press enter. 13.4998. And the last question here on the notes that we have to solve for is question 14. So it looks like we have negative 6x minus 1 equals log base 3 of 243. Well, let's go ahead and let's change this guy right there. So it's going to be log of 243 over log of 3. That's equal to negative 6x minus 1. Got to go ahead and add the 1 to both sides. You got to get rid of adding and subtracting first. So negative 6x equals log of 243 divided by log of 3, adding 1 to this whole thing. Then I can go ahead and divide by negative 6, but I need to divide all of that by negative 6. It's the whole thing. So I don't know how you would like to write it, but usually if you have fractions on top of fractions, I start to switch over to dividing as a diagonal line, which is fine with me. So our generalized form, x equals log of 243 over log of 3. I got to go ahead and add 1 to that fraction. That all has to happen in a certain order. And then I get to go ahead and divide by negative 6 here at the end. So that diagonal line dividing, that's our generalized format. You might have to do something like that for a test, but again, we won't make it that difficult. But if you can do a problem like this, you can do any problem. Let's figure out what that is as a decimal. So again, I need to trap this entire thing here first. So log of 243 divided by log of 3. Notice how I'm closing the logarithms as they appear. I have to go ahead and add 1 to all of this and then close it. That's the big group up front. Now I can go ahead and divide by negative 6. If I hit enter, I get negative 1. X equals negative 1. Why? What is going on? How can we get such a perfect number out of all this crud? That's just insane. Well, if we think about it, go back to this original problem. Let's write it in exponential format. All right, so let's try exponential. The base was 3. Then I have to go ahead and take it to the negative 6x minus 1 power. That's the exponent all the way over here. And that's equal to 243. 243 actually is a perfect number. I bet you wouldn't have guessed that. It is 27 times 9. 9 is 3 times 3, and 27 is a triple brancher of 3, 3, and 3. You don't have to have this down. I'm explaining why it works. So 243 is 5 3s. It's 3 to the 5th power. This is 3 to the negative 6x minus 1 power. Notice how my bases are the same. If they're the same, that means the exponents must work out to be the same. That means negative 6x minus 1 has to be equal to 5 in order for this to equal out and to balance. So if I'm going to solve that, adding 1 to both sides, I get negative 6x equals 5 plus 1 is 6. What? I divide by negative 6, and I get x equals negative 1. Crazy. That's absolutely nuts. So sometimes we can get decimals, which means we wouldn't have been able to think of that number on our own. But if it works out to be a perfect number, a nice whole number, we should probably be able to get there with our math. Kind of nifty. And the very last problem, okay, you're just filling in these spaces with numbers and trying to figure out what your individual problem would be. So I'd encourage you guys, choose a problem where you have either a plus or a minus sign down here. Maybe fill in these boxes with numbers that you just pick out randomly, or better yet, you could even roll a dice and put numbers in there, and then go ahead and write your generalized form, and then figure out what that would be as a decimal. If you can do your own problem, you truly understand the material, and you'll do very well in the homework and the quizzes and the test. Excellent. If there aren't any questions, I think you guys are going to do great. Email me. Let me know, and I'll try to help you out with in whatever way I can. All right. Hope you guys are doing good, and we will see you in a bit.